Hello again. In this video, I'm going to go over this homework problem from 8.4. So let me just read through the problem and I'll show you how to work it out. It says data show that men between the ages of 20 and 29 in a general population have a mean height of 69.3 inches with a standard deviation of 2.5 inches. A baseball analyst wonders whether the standard deviation of heights of Major League Baseball players is less than 2.5 inches. The heights in inches of 20 randomly selected players are shown in the table. Test the notion at the 0.1 significance level. Okay, so this is a hypothesis test problem. And when you run a hypothesis test, the first thing you should do is write down the claim mathematically in symbols. So in this case, you can see that the claim is that the analyst wonders whether the standard deviation of heights of Major League Baseball players is less than 2.5 inches. So they're claiming that the population standard deviation is less than 2.5. And the symbol we use for population standard deviation is sigma. So symbolically, you would write the claim down as sigma is less than 2.5. And I would label that as the claim so that you can remember that. And of course, since this has a less than sign in it, that is your alternative hypothesis. And then the null hypothesis is that sigma would be equal to 2.5. So that's your H sub 0. Okay? But again, I would label this as your claim. This one is the claim, the alternative hypothesis, in this particular case. Okay. Now, when you run a hypothesis test, we have two methods to run the hypothesis test. You can either use the traditional method or the p-value method. In this case, we're going to use the p-value method. So let me show you how to do that. So when you run a hypothesis test using the p-value method, the first thing you have to find is the test statistic. And the test statistic in this case is a chi-square value. And the formula for it is n-1 times s squared over sigma squared. This is the test statistic that we use when we make claims about standard deviations, population standard deviations, or population variance. Okay, in this case, the claim is about a population standard deviation. Okay, and so that's why we're using this test statistic. Okay, so we're going to run the test now. Now, when you run a hypothesis test, you always assume that the null hypothesis is true. Okay, in this case, the null hypothesis is that sigma is equal to 2.5. Okay, that's true no matter what hypothesis test you run. When you run a hypothesis test, you always assume up front that the null hypothesis is true. Okay, and then the test statistic is based upon that assumption. Okay, so in this case, we don't know what the real population standard deviation is, right? We don't know sigma. Sigma is not known. The only way we would ever know that is if we looked at the heights of every single Major League Baseball player and we actually calculated the population standard deviation in those heights. And we don't know that. Okay, we don't know the heights of all the Major League Baseball players. The only thing we know is the height of the 20 Major League Baseball players that were selected at random. Okay. And so we need to know what the sample standard deviation is for those, okay? But again, even if we don't know this, right, we don't know sigma, the assumption is when we run the test that the null is true, and so we're going to actually assume that sigma is 2.5. Okay, and then we also need the sample standard deviation, which is S. And of course, they didn't really give that to us. All they gave us was the raw data. So if we go back to the original problem, if you click on this table, these are the heights of the 20 different Major League Baseball players that were selected at random. we need to know the standard deviation in those numbers. So to find that, you can go to your calculator, and what you can do is you can go to Stat and then select Edit. Like you have this menu of Edit, Calc, and Test. Make sure you're under Edit, and then under the Edit menu, press Enter under Edit. And then just enter the data into L1 like I've done here. Okay. Now after you enter the data into L1, I want you to go back to Stat, but this time go to Calc. And then under that menu, select one variable, Stats. So press Enter. And then you have to press Enter one more time. And then it gives you all this statistical information about the data that you entered into L1. Notice this is the mean of the data, X bar. But what we want is the sample standard deviation, which is S sub X. Don't get that confused with sigma sub X. Sigma sub X is the population standard deviation, if this were a population. But it's not. The 20 people that we selected are a sample. Okay, this is not a population. The sample is of 20 people selected from a population. Okay, so this is actually a sample. So you want to use your standard sample standard deviation here. And that's where I'm getting the S from. Okay, that's my S. They didn't give it to you, so unfortunately they didn't tell you that. So you have to actually calculate it on your own, and you can do that on the calculator. Okay, so now let's find the test statistic, chi-squared. All right, so it's n minus 1. N is the sample size. In this case, it's 20, so it's 20 minus 1. There's your sample standard deviation. And then you have to square that. And then again, sigma, we don't really know what sigma is, but we're running the test under the assumption that it's 2.5 because we're assuming the null is true. Okay, and so that's 2.5 squared on the bottom. And now just let's go back to the calculator, plug all that in, and see what we get for our test statistic. All right, so this is 19 times 2.11268, or 26 and then 18, 729. Okay, and then there's your square button, so square that. And then divided by 2.5 squared, 2.5 and then squared. Okay, and you can see you get 13.568. Okay, so that's your test statistic. Okay, now we're going to find the p-value from the test statistic. And so chi-squared distributions look like this. They're not symmetric. They look something like this. Okay, and then what I'm going to do is I'm going to draw this test statistic on the now chi-squared values go from 0 to infinity. And so what I want to do is I want to draw this, locate this on the chi-squared distribution, this number. So they're always positive. There are no negative chi-square values. Now, the question is this number towards the left or towards the right in this little distribution? And here's how you can tell. If S were equal to 2.5, if this actually were 2.5, then you would have 2.5 squared on top, and that would cancel with the 2.5 squared on the bottom, and you'd be left with 19. That's the middle of this distribution. And so 13.56 is actually to the left of that middle piece. So it's somewhere over here. That's my test statistic. So this one's actually towards the left side. Now again, and the easy way to find this is anything above 19 is going to be towards the right side. Anything below 19 is going to be in the left side. And 19 occurs when S is 2.5. So another way to look at this is to say anything less than 2.5 here is going to be to the left, and anything above 2.5 is going to be to the right. Okay, and so obviously this is less than 2.5, so it's going to be to the left. That's the easy way to tell. Okay, like if S had been 3, okay, then when you plug 3 into here, you'll get 3 squared over 2.5 squared times 19. That number is going to be above 19, so it's going to be more towards the right. Okay, and we know that because 3 is above 2.5. Okay, and again, if S is less than 2.5 like it is here, and then when you plug it into this, you're going to get a number less than 19, and it's going to be towards the left. And that's what's happening in this case. Okay, so having done that, we're going to now find the p-value. Now the p-value is actually the area in the little tail here. Now if this had been on the right side, then it would be the area in the right tail. Okay, but this one's in the left. Okay, so the p-value is the area in here. The p-value is this area, so let's find this area, and I'll show you how to do that on the calculator. So to find it, go to Distribution, and then scroll down to chi-squared CDF, and then press enter. Now, the way this works is you have to put in the left chi-square value and then the right chi-square value, and then the degrees of freedom. So we're trying to find the area between 0, a chi-square value of 0, so that's going to be my left value, and then comma, the right value, which is 13.568. So 0, comma, 13.568. And then comma, the degrees of freedom. And the degrees of freedom is always n minus 1, so in this case it'll be 19. And then just close your parentheses off, and then press enter. And this is the area trapped between these two chi-square values, the lower one and the upper one. Okay, so the p-value in this case is 0.917. Okay, that's our p-value. Okay, and then once you find the p-value, you're going to compare that to your significance level. In this case, our significance level is 0.1. And if the p-value is greater than the significance level like it is here, then you fail to reject the null. Okay, and then let's make a conclusion about the original claim. So let's go back to the original problem. So if you fail to reject the null hypothesis, it sort of indicates that this is a plausible hypothesis because you're failing to reject it, right? So it's very plausible that sigma could be 2.5. And so if this hypothesis is plausible, then there's not sufficient evidence to support the alternative, which happens to be the claim, so there's not sufficient evidence to support the claim. The only way to support the claim in this case is to support the alternative because they're the same thing. The only way that's going to happen is if you actually outright reject the null hypothesis. If I reject the null hypothesis, then in that case, I'm saying, well, then the only other hypothesis is the alternative hypothesis. And so that would mean there's sufficient evidence to support the alternative, which would be the claim in this case. Okay, but we're failing to reject the null. And so a failure to reject the null, again, means that the null hypothesis seems to be plausible. So you're kind of hanging on to this hypothesis as a possibility. And if that's the case, then you have no evidence to support the alternative hypothesis, which happens to be the claim in this case. Okay. Notice here, this is the test statistic. This is the p-value rounded to 3 decimals. And then down here, they just mentioned the same thing that we just talked about. If the p-value is greater than the significance level, you do not reject the null hypothesis, and that means there's not sufficient evidence to support the claim. Okay, one last thing. It's probably a good idea for you to get some kind of understanding of what the p-value really is. The p-value is the probability of getting the observed sample data randomly if the null hypothesis is true. So remember, the assumption that we made before we ran this test was that the null hypothesis is true. In other words, we're assuming that sigma is 2.5. And what the p-value is giving you is the likelihood of getting the observed sample data, which was this, randomly, under the assumption that sigma is really 2.5. I mean, if sigma were really 2.5, right, that's the assumption that we made. If that were really true, what's the probability that you would end up with a sample that looks like this, where n is equal to 20, the sample size is 20, and the standard deviation you get from that sample is 2.11. Well, the probability of that happening randomly, assuming that sigma is 2.5, the chance of this happening randomly over here, this observed sample data, is it happens with a probability of 0.1917, which is about 19% of the time. And what the significance level is it's a boundary that you establish up front. The statistician establishes up front, and it says anything below this significance level is considered highly unusual. So anything less than 0.1 is considered highly unusual, right? Anything less than 10%. But that didn't happen here, right? We got 0.19, okay? About 19%. So this is not considered highly unusual. This sample that we got is not considered to be highly unusual under the assumption that sigma is 2.5. This happens 19% of the time, randomly, if sigma is 2.5. So it's not considered highly unusual. It would have to be less than 10% of the time, right, for it to be considered highly unusual. And that's what the significance level is. It's a predetermined boundary that establishes what we consider to be highly unusual. And so that's why we always compare the significance level to the p-value. You know, if this p-value had been really small, like 0.01, right, then that would say that the probability of getting this observed sample data under the assumption that sigma is 2.5, the probability of that happening randomly is about 0.01, right? If that were the p-value, that only happens 1% of the time. And so that would be considered highly unusual because it's less than our predetermined significance level up front, 0.1. And in that case, if this happened, you would reject the null. And then there would be sufficient evidence to support the claim in this case. Now, again, the reason you're going to reject the null in this case is because we don't believe that this assumption is true because the p-value was so small, right? We don't believe that sigma is 2.5 because we got an S value that was so far away. It occurred, the likelihood of it happening was really, really small. So we don't believe the assumption in that case. And if you go back and look at the original hypothesis setup, if you reject the null, then you're supporting the alternative, which happens to be the claim. So you're also supporting the claim. Okay? So again, if the p-value is small, then you don't believe your assumption that the null hypothesis is true. That's why you reject it. Because it's happening, the likelihood of getting that observed sample data is really small under the assumption that the null hypothesis is true. So that's when you reject the null. If the p-value is greater than the significance level, then you fail to reject the null because it's very plausible that your null hypothesis could be true because the sample data that you observed, was not considered to be highly unusual under that assumption that the null was true. Okay. So I hope you found this video helpful. I'll continue to work problems out from the homework, and hopefully you'll get a chance to look at some of my other videos. Until then, bye-bye.